Um, so before we go to the content, so there's an important change of the schedule. The next lecture is starting in the morning from 9:50 p.m. to 5 p.m. Okay? Not p.m. a.m. So in the morning, start 9:55 a.m. Okay? I have to leave right after the meeting to Canada because unfortunately, yeah, I mean, if I change the date, somehow flight ticket is like a become double, so I have to change. Um, so that's the can you change the set? The room is the same as before. Okay. So please tell your friends if they are not around. Also, I can send a message via WeChat. So and then, so let's go recap. What we have done last time, the data is integral and two parts. So let's recall a little bit. So we talk about the green function. Time ordered correlation, 2-point correlation function. Okay. And then the time ordered correlation function, which satisfies once the Schrödinger operator acts on G H function, you get the delta function. That's the most important property of the green function. And then of course this correlation function, so the expectation value is always can be done by choice of pro particle. And the density matrix and then take the curve. Once the definition is statistical mechanics. And the rho hat is taken to the ground can bound sample probability. And then so the normal, so this is the case. So therefore, once you take the Fourier transformation of so G alpha beta, and then this is the G alpha beta, R T of E is minus K R minus and then plus omega T plus T plus. If you just take the first transformation, so this and it acts on the yeah, and then so G RT is equal to E is the volume of the plate. Okay, as infinity to infinity. Then omega E to omega 3 plus minus omega T. Now, if you take a Fourier transformation and act at this Schrödinger operator from here, what you get is that the first sum of K what was that? The omega. That's like it. Okay. So here, the equation I just give you are following. type detail. So this is just a delta function. It's a delta function. Right outside here, you just can be written like this way. And then, so now, therefore, from here, you can just alpha beta, just get omega. So note that the omega here, out of the time derivative, this part will give you dk minus dk, and then plus 2. Therefore, this will give you the alpha beta. And then you just need to add something like this. So this is the this part coming from causality. This part comes from causality. So later, keep the tension. 因果律。Later we consider so-called advanced and the retarded green function. In that case, this part becomes a slightly different. It's slightly different. Anyway, so that's we will see later. So this is non-interactive. So this is non-interactive. And then, so we also consider final temperature function. Okay. So here, we consider that time and tau and periodicity. So literally imaginary time becomes like a circle with circumference later. Later. So that's okay. So what we saw is that the this G alpha beta R and on time and tau. Tau is essentially harmonic product is equal to 3. And then R and R prime tau plus beta. So that's satisfied. And then not exactly equal here, we have to force something like a sigma. So sigma. So when you identify, if you once go around the time circle, imaginary time circle, the correlation function will flip the sign. This is the periodic. So you have to also put the anti-periodic boundary condition on the Fermi. So this is the bottom. You get periodic and the fermion anti-periodic. For time circle. Okay. And then And if you use this rule, so you can write down the G of A or instead beta inverse sum of E minus omega n and G of beta or prime of omega n. Right. Okay. So since here time circle is finite, so that omega n is quantized like 2 pi n over 3 beta, and n is what? Fermion. So here n is odd for fermion, and even for boson. That's how it is. And if you use this, and then G alpha beta, G alpha beta, and tau, sorry, Fourier transformation in time circle will give you a force. So if you want time minus beta 0, E I omega n tau, and G alpha beta, or prime tau, and plus 1 U beta, E I omega n tau, G alpha beta, or prime tau. Okay. Now we change it here. Is that you can just okay? Let's only focus on first line. So first line is equal to sigma over 2 minus beta 0 e to the I omega n tau and G alpha beta r prime tau plus beta. Okay, so tau plus beta. Because I used this periodicity with the shift by beta time circle, and we find that I'm saying tau theta is tau plus beta. Then this one is equal to sigma over 2 minus beta, 0 to beta e to the I omega n tau r, and then minus beta. G alpha beta. Okay, like this. And okay, so now from minus beta to 0, integral becomes 0 to beta. From 0 to beta. Okay. So now one can combine them together and to get so that the entire thing is equal to sigma 1 plus sigma the beta like this. Okay. And here, so we pose the beta to the odd for fermion, so they cancel each other. In fact, so this is for fermion, this is minus 1, and this becomes also minus 1. For boson, this is plus 1, and this also becomes plus 1 because of this condition. Because this condition. Therefore, this is total becomes 2. Therefore, you can erase in fact this part. And this is equal to this. Fine, so Any question at this moment? Yeah. Fine. And previously we write down the G, R, and then D. To be as follows. Well, what we saw previously, this is just a new definition of the given function in the time. Sorry, so this is finite temperature given function, and then so f of x here is f of e. And of course, like a e to zeta, which will came out of me, plus sigma, minus stuff. So minus sigma. And plug this one into here. Plug this one into here. One can say that it's the Fourier transformation of this. So now for G, omega, omega n is equal to R D R equal to beta E in it's just Fourier transformation. And then here's as I mentioned, from 0 to beta, coming from this one. Okay. And plug this one into here, what you did in the point. So if this integral is here to beta, so it's always the relevant part is the first one. Down here. So this is giving 0 beta. The tau e to e on omega n of r. Sorry. It's from n minus u. Okay. 1 minus okay. And this one can be written followed. So this is just simple integral, so that the, you can perform this integral. Then you have omega n plus. Like this. So if you perform this integral, you get the denominator, and then this is from 0, the n, and the better the first term is come from upper end, and bottom one term come from bottom end, and just multiply one minus it. And this is simply equal to I omega n k plus mu divided by plus. So that's the Fourier transformation of this green function. It's very simple. We just only change it that in the previously this was omega, and then do the friction plus I delta sign or something like that previously, without the final condition. Any question at this moment? Okay. So let's take a look at the meaning or like a property of this green function. Property of this green function. It's just review of last time. I'm just refresh your memory. So there's a so-called Lehmann conception of the function. So here, G function is green function. So let's consider the n is the open subset of states, and then to insert the definition. G alpha beta T. So that's the first term, and then another term is the sigma They're very similar to what we have. Okay, like this one. So just put the complete basis in this between the operator, these two operators. Okay. Okay. So then, so here is H stands for what? H stands for what? It's a good question. I never picture. So the time translation is just sandwiched by unitary time conversion. So the output, so one can just write down the following. So this is equal to sum of Fn. Okay. So here, you can just get coming from here. From here, you can get e minus plus I e m e prime and so on. So the opposite here. And then this is given by here. Okay. Sorry, I made a mistake. So it's not only the and I think you should get the ground down sample. Somehow you should get the pull up. Here you should get plus mean. Let me see. So here you should like this way. Let me Oh, sorry. Something strange. Here's no last me. This is just the T, I think. And this is last. I don't know which one is the last institute. Yeah, I think maybe this is okay. Because the n here is equal to n plus 1. So the particle number here of n is And if you act this correction operator, it increases the particle number by 1. Okay. So therefore, and m is plus 1. And n plus 1. That's the channel. And you have to be taking care of the difference. So here is just plus 1. And this is 0. And then here you have to put the view here and out front. Sorry. Yeah. So I think that's what you need to do. So the difference, so why you have only here minus mu and this is without mu is because of this. Because of this relation. So it creates the one particle by side dagger and then another is one particle by side. So therefore you include one by here and not here. Okay. And you can just write down like this. Fine. And as always, the function is better to move. So you can use the theta function to be so theta function last time we used this identity. Minus infinity. Like this thing. And this is Fourier transformation. This is Fourier transformation. Let's see what's going on. Okay. So if you do the first transformation in time direction, this one, and plug this one into here, and use this identity. Use this identity for that function, and what you get is and this is equal to number G sum of n of them. Okay. So you can combine that you can just write down like this way. And then perform e to the minus omega blah 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 e integral will give just delta function, and perform omega integral. What you get is a following. I will suppress the coordinate here. Okay. Sorry. Here, I need to fix. So that's what you get. So here you just be careful about the holding minute time a little bit, and then so this is called Lehmann representation. Of screen function. So we'll see why it's important in coming half an hour. So we can do the same thing. So in the case of the, so this is just a non-interacting case, and then for the final temperature, case, well, so just replace by T by tau. On prime, and then here you just have there's no I here, and there's no I here. Don't stop. So that's it. Already. This is outside. So just here, erase I here, and then replace T by tau. That's the final temperature. And then, but we saw last time, so it's just a Fourier transformation is just giving only omega. It's just 0 very odd. And like this time here, essentially what's relevant is only this part. You set the tau prime to be 0, and the positive part is coming from here. And this is equal to 1 over C, T, 1 over M, E to the there, and then is coming from, it's just coming from here. And then upon this integral, let me go. 되겠습니다. Sorry, I think I made a mistake. There's no minus sign. It's just, yeah. So basically, so note that this, so this one coming from 0, and this one coming from the alpha n. So you have to integrate from 0 to value. Essentially, what's the d tau integral c is e to the I omega n tau, and also e to the this one. That's essentially what this d tau integral will do. And once you do the integral, you get the denominator, and from the end, bottom end, you get the 1, and upper end, you get the plus sigma. Sigma is coming from, so this sigma coming from e to the I omega n beta. Better. And then, and this one, so if you use this relation, capital Nm is equal to capital Nn plus 1. Okay? If you use this relation, this can be written as follows. So 1 times this way 2 and plus sigma. Now, En will be gone. Like this. So here, if you multiply n, minus mu and n minus mu is equal to minus mu and n. So the subscript will change from n to m. Because of this relation. Fine. So this is the finite temperature case for the green function, Lehmann representation of the green function. Any questions at the moment? Okay. So now let's introduce so-called notion of retarded grain function and advanced grain function. Yeah. And its property. So retarded grain function of omega, and then our e R5 P prime is given by 5 theta plus P prime. Like this one. So here you have just quantitative of the operator and salary. I mean, let's content. Like this. So this is retarded because I mean tau has to be greater than tau prime. Okay. And then here is tau prime is greater than it's 5 months. Okay. So the definition of the this green function. So you can just name. You just name for the function. And let's consider the Lehmann presentation of the. You can do the same exercise as before, but now you have to be a bit careful about how to do that because here. Okay, so that's you have to be careful here. So here you just have to. So this is retarded. Then it's hard to tell why it's so retarded because I mean here is something like okay, I will change. Let's take it the I mean here if you look at system, I mean it's kind of like how prime we have a creation occur, and then it just moves to tau t, and then there's another. So on the other hand, here it's more like there's a creation of the antiparticle, and then just move to t. It looks like that. So I don't know. This looks like more like a restart. This looks like more for me. That's why I just got complete. But anyway, so let's accept this as a definition. Okay. I don't know why this terminology will be used. Yeah, so the dagger is always creation operator. So here it's like the antiparticle is created by tau. I mean, it just moves the antiparticle to the from T to T prime. Here, just the ordinary particle go from T prime to T. So anyway, but anyway, so let's accept this definition. It's just definition. Name is just name. And then let's focus on the retarded one because the last one is the same. And if you do that transformation, it's almost done before. same as before, except here, you have to be careful. All the calculations same, except this becomes plus. So to derive this, what we use is that here follows. What we use is that the same t minus t prime is minus infinity to infinity e to the I omega t minus t prime, and then omega plus I delta. That's what we sort of use. And then it used to be here is this term coming from Taylor's t prime in the ordinary Green function, whereas this term comes from Taylor t minus t prime. But on the other hand, here for retired Green function, we only have a theta t minus t prime. Therefore, if we change to, let's see, G here, then we go to the only two differences, this becomes 1. That's the only difference we will get in the kind of calculation. Purple is not good. Yeah. Insert it, and this becomes 1. Okay. So now we can mustache to re-ravel. We can re-ravel n and m. Here. I don't want to erase here, so let me write down. So this GR alphabet R T of prime T prime, which can be repackaged into the following way, the more nice way. And then, so here you just rename M as a N by M. Then you can just repackage into very simple form. E to D minus layer and minus D plus minus E to D minus layer M minus D N M. Sorry, this is plus sigma. Or plus sigma. Yeah, maybe I should call it sigma. Sorry. Like this. Okay. So you repackage into one single term. Okay. And then we I think I will make it. Okay. And the reason why I introduced this retarded one is if you compare this one and this one in percent. So I now will take anyway. The reason why, so the form of here is almost same as this one. So E to blah blah plus sigma, E to blah blah, and then this one. E to blah blah plus sigma, E to blah blah, and this guy. And the only difference is that here is slightly different. I times omega n, whereas this is the omega plus I down. That's why. So this is finite temperature grain function, finite temperature, and this is just more interacting time with ether. But so you can relate them by finite continuation. To make they are related by the continuation, so it's called balance for spectral function. Spectral function. Thanks. Like this. So this is for spectral function. If you introduce this one, you can just write down this one is as so this one, let's call it finite temperature of finite. Finite R or prime on omega n. It's just a Fourier transformation. I mean, whereas G retarded like this question. So you can just repackage for two functions, just change the I omega n here for omega plus I. What's the okay. Any question before? Moreover, so you can introduce the D operator. So it's just another way to write down. This is something about. I don't know, maybe 2 is better. Then, so D alpha. Return it. So this is the G finite. What the expression? So if you introduce this function, you can just informally you can informally the retortic green function and the final temperature green function. That's a good point. Okay. Okay. Any question at this moment? So if you only look at the final temperature, but here you have the ambiguity here because the green function here is the here discrete value, so that the multiplied. So this d alpha beta is multiplied d alpha beta times say e b. Like a 2L beta. So 2L beta. The omega n is a product of 2 beta, 2 pi, and 1. Okay? So that's what the definition for omega n. As first we call that the first thing. Yeah. So now for immediate size, so this is the beta d. If you just shift by e to L is some integer, and beta d, and plug this d is equal to I omega n. So this is just 1, right? So this is just 1. So now for there's the ambiguity of doing this function for finite green function. But this can be fixed by just imposing some boundary function. I think now I can write here. Okay, my boundary condition. So we can just show that the when this omega goes to infinity, G alpha beta entirely power of time omega. So if you use this, so if you use this relation, if omega is big enough, so the dominant term is become, so this term can be negligible, so this becomes dominant. So therefore, you can just extract out from the integral 1 over omega, and then minus infinity omega tilde will also better prime on the and plug the definition of the spectral function is here, right here. And this is 1 over omega, 1 of m. And you plug that into here, what you get is that the En minus mu. Like this thing. Okay. And this one can be written as follows. So this is 1 over omega. The first term is just a sum over n e3 minus beta n minus min n, and then n side diagonal. Whereas the second term is sigma over omega, sum of m e3 minus beta epsilon m minus mu minus n, okay, and m side diagonal side. So now I just get rid of all. So normal basis. The first time I just remove the n part because it's just 1. The second term I just remove n part because it's just 1. I mean, I just use the like this. So I use this. First term I just remove complete basis n. The second term I just remove complete n. And just rewrite. And you get this. And then, what did you notice this one? So this is just one over omega psi average. Like this one. So this is the this is Boltzmann weight, right? In Grand-Canacano stuff. You can treat a rho. So this is essentially trace of rho and side diagonal. First term is essentially. The second term is just almost like this. Up to sigma. So therefore, it's just excitation and computation. And we know this one is alpha from computation. So therefore, this is equal to 1 over omega delta alpha beta delta alpha alpha. Like this. That's what's good. So if you introduce capital omega goes to infinity, these z functions behave okay, so if you plug this on omega and like this way, it becomes delta function. To get the delta function, you plug this one into here. Delta function when omega equals to 0. So this ambiguity will be removed. In any case, so what I wanted to say is that this The reason why I introduced retarded green function is because you can just analytically continue retarded to finite temperature green function. Any questions at this moment? Okay. A little bit slow. Okay, but it's okay. It's okay. Maybe let's take a break for 10 minutes or something. And if you have a question, just. I mean, these will be retarded sorry. Green function will briefly appear even in the PCS theory. So I just prepared repeat this theory. And also, we already introduced density functions into density metrics and operator. Sorry. Price of system will give you expectation value. Okay? And then the most basic expectation value in the statistical mechanics or quantum physics is this green function. So I mean, it's better to learn something basic about green function. Because I mean, everywhere you have to use green function in statistical mechanics and quantum physics. So and then yeah, anyway. So even if you take the quantum physics, you will learn this Lehmann representation, and then the beginning of the second half, I will introduce the meaning of this spectral function and why this Lehmann representation is. Okay, let's take a break for 10 minutes.
就他是他，因为咱们求分的时候要比较长的，是这个，做这个的时候就是把，应该是做这个的时候是把这个跟分没关系，这个是对，他应该先交换一个指标，先把这两个交换这样，对，对，对，用的还是正式用的，对，因为这个它叫指标，这个目标。就把这个后面全给我对吧？就是那个对，所以这一个地方，那么这个理论的话，是啊，就这个地方是属于就是这样这个推荐来的，有个性，这个我会知道，我这两个只有这个地方，没有知道其他地方就是。国家这里头，这个而且你看要不是你看我明天我愿意这个是这个微博上也是这个什么表示，它就是也就是这个现在看法量最少，那法量最少。第二个是内光线，一旦速度协调的不成，有什么干嘛？知道吧？没有阿尔法简单就是很多，但是历史的话，还是历史的话都在一个完成一下，这个区别那就是因为我们的发展在哪？我觉得法就是你的法要解释到，它属于一个你把不能求普及了，你要求实味以上，这样子他玩知道能半天最大了。这个分别的来源那我这个这个你要给哪种？因为但是你的性格多成还是快乐多的话，但是你100多次吧。 这个可以这条要这个 F 加内部加 F 加的后边定出这个，这个有什么例证是，然后我去带入这个形式，就这个什么发生差别或者第二个就是 I 对的，像这个 I 对，我打算今天发明一个这个很就是人家以前那个有各种电脑自家东西。另外一个一直是这样。这个 I 5加会加一，每人加一个，这个2。
只有在这里，
这边这个对，就是重心就是在这个，也是那个通会下好，一个。这个片子里反正是，你到回家这就是说，或者是说他这个是受病的是，不是你看他或者是说，没有讲这个一些项目目标，就是近期就这个，那个你发刚就这个，就是这个就这样标，就约定这个。哦，这个好像是下台啊，它给的影响页面，就变这个东西。这个东西就在一小这样球这边没有，像这个的球就是在，要是你是这样，后面一些是这样。这个定义就这个相应中，这个是那个我存代码，那个single 状态，这个可以。这个情感之前我去他的，就也是那他就这个两张，一个有这个是一个另外3个是这个。大家定了，你还是下一句，他其实给这个就这个地方是这个
This omega is different from this one. Then you have the integral of this delta function. That is
带一点就一个那个。
就是为什么那个
是有一个手法，要是相差超过一个例子，对，对，就是这个降速，这个方法，降速啥？它降，所以这个给它降一定，因为它的降是所以它才降下。说话就直接我也没弄，为啥这个最好有点你可以找知道按这个物理机制我最想还是那个就是就像是那个这个地方就是它这里的欧米伽和你这个还有这个对欧米伽所以那边要做一个分然后自然就是利用那个表达特性用那个筛选就行了基本上一个地方这两个欧米伽是不一样的非常不相对它这边这个地的 M 应该它这个都需要另外一个地方但是两个都是在给你都往南上一片看透我就知道看见了这玩意儿可以直接我这上没打这样的我知道他在搞他可以他最开始讲是公司没看到就讲就说这是那个定义对然后这是确定个方程对这确定个方程然后这是指这个傅里叶变化然后这不是的反傅里叶奥所以觉得差的符号然后那这个是这个确定方程模你带哦，就是把这个 G 阿尔贝塔带到确定方程哦，就是变成了那个频率上的是吧？对，哦，变了哦，所以这个前面这一条出来讲的对的是对的，这样出这个这样出是 1K， 然后这样出是1对，我这个特别慢一点，然后。然后这边就把这个东西都是对，然后这里面就两个积分里面都已经对，哦，那很好，然后这个英国摄影我觉得真的没有关系，对。这怎么说？这个是时间它的套啊，它是个时方式，也可以。我也觉得就是对时的对应的温度。那我问题就在于这个地方，那个套的 IT 没有对象。对，被套的。我这里对，它是时哦，但说这题是虚的。这只是个对应，对，它只是对应。那我问题在这个地方，这个孩子宝贵景。对，那就他们既然是10的话，他不应该他的工作吗？那不应该有的，就是他不应该有的。
这个超级
那就有问题了，那后面怎么对应没问题？或者感觉这也是一种对应关系，这个当然。就是那个一下这个其中的导你定一个也是不错的，也就是一个公式也是做上对，然后如果它是个10的话，那负极变换你是都会有这么激烈的那个那包括你这个地方对它做粗劣什么，那还是你等I我你干套是吧？它还是这么行。
那套是。
对，就可以。我们试试这样。保持我感觉这个，保持健康
我这应该提出一个
这是他说的，就我觉得是个对应关系，因为它本身它其实反映的就是我就是一个
人可以给他改。对，你那个局其实是有根本意义。觉得我说的这个好就
咱们它会本身这个事情是从那里头，就是比如说是有业一比一它怎么变，套我们
然后你右边的这个市场上的改变，就是它的这个地方的一个这个雷达啊，对，
然后这个东西它说它会相当于一个虚的实力，但总之它越
这是很
那这样子能不能导致它对怎么会两边变成什么？
那从这两个是非常多，就是就是来去吧，
对上来去吧，
对，
那就没得
是的，那个题就是应该不是这个意思，就是，但是这个在这个东西里面，这个背后应该是个实的。
对啊，这个是配合还会啊，我感觉这几个对，你就是对应关系，不是你非要对应到这个方式里面，就是这样。
好，OK，已经 OK，稍微OK， so now from now so to understand the meaning of this spectral function and then why Lehmann presentation is important. So okay. So I will raise so again. So the next lecture will take place on Sunday morning, Sunday around 10 a.m. So even if you come on Monday next week, I'm not going to be here. So yeah, be careful. Anyway, so if you cannot make it Sunday morning, again, I'll record this lecture, so don't worry about it. You can always. Okay. So now, suppose you have the system is the translationally invariant. In that case, sine alpha r can be written e to the minus I equals r sine alpha 0 e to the I. We can do the translation operator to if the sandwich is same as the Heidelberg picture. So you have a translation operator, you can always put all the operator into the origin. You can have whatever. Translation operator means the physics studying here is the same as physics studying here. So that's what it means. So that's cool. Whatever is, I can always move these students to that seat or these students to that seat. Anyway, so you can bring always the operand to the option by this operator. If you do that, okay, I think it's too straightforward to do that. So the lemma is so far we just write down G, R prime and then omega. So we just write down like this. So return this one, R prime omega. But this can be just Fourier transformation. Fourier transform to this like this. I'm not going to write everything, but it's too straightforward derivation. So but it's just a simple exercise to do that, which is the this length equal to. So okay. 60. Like this. Sorry, this is plus. If it is retarded, you can derive this one very easy. I mean, I'm not going to derive everything. I mean, it's super easy exercise to do that. I mean, here it used to be. So this part used to be sorry, n psi m. Here it's just r and m psi dagger and r prime and then it used to be like this. But now if you do the, this transformation, what you get is that the n psi 0 m psi dagger 0 and e to the whatever I, p, blah, blah, blah. Okay, n minus k, m, t, r minus r prime. And I don't remember plus minus anyway. So you get the extra pieces coming from this sandwich transition operator. Oh, is equal to this value. And perform Fourier transformation with respect to R, you get this dot function, delta k plus blah blah blah, delta function, and then so this part becomes just a no curve because then it's the affirmation function. Okay. Fine. Now also we can just introduce so-called, it used to be the spectral function is okay r prime, but because r independence comes from here, r prime coming from here, and so on. But now we can use the spectral function is also completely fit a Fourier transform to k and omega. And this is equal to b. Existing. Okay, so that's what you can do. And then, so that's different from, yeah, so here I changed a little bit. So it used to be dependence is the R and the R prime. Okay. But now this one is just using the same trick I told you about over there. You can just rewrite everything. Fine. And using this spectral function, so this is G final temperature. Okay, omega n is just that. Like this, and then R with omega. I don't know, like this, so you can just forward that. Okay. And as you can really see, if you look at this wall, so the spectral function, so yeah, spectral function is now real. It's become real. So this is already real, and all the quantity is all real. And then green function looking at here, so let me. Okay. So green function is here, there's the I here. The I here is still complex. But I mean, you can use the following trick. The principal value is 1 over x minus I pi was down to 1. So this is the constant. So P is the constant principal value. And then we can use this identity to show us the rho k spectral function is the imaginary part of the function. Okay. So now, do you understand what I mean? So, do you know how to get this one? Is it okay? Sure. From this, is it from this? So the first one is just immediate. I mean, this part is the same as omega, this part. And then if you take the x to be this guy, x to be this guy, you get the delta x. At the delta x, you will get this quantity, this quantity, 0. However, for this guy, the n and m are opposite. So n and m are opposite, and so this is opposite to this one. You have to switch the role of n and m. To do that, so here you have the delta omega minus en plus en plus mu. But if you put this one, omega is the if you plug this one into here, you get that plug this one into here. So e to the minus theta plus en plus en plus mu. You get this one. And if you just multiply this one, so this minus en cancels with this en, and it is, so what's left is this one. So it becomes em plus em, and then n plus mu is just become nm. Yeah. Like this one. I think I better sign out now. Okay, everything okay. Yeah, it should be okay. Sorry, I think something's finished. Omega is equal to, I think there must be sign was wrong. Is something funny French? No, I think everything should be correct. I think something's strange. No, it should be consistent. My sorry. And I want this one to be mine. I think there's something strange in my note. Sorry. Sorry, I think I made a strange. Something strange. In any case, what I want is that so this part becomes e to the minus beta, m minus mu, and m. So then the rho n and m are swapped. You can just take the term corresponding to this. So that's what I want. I think I made a mistake somewhere. I don't know. I cannot find out this moment now. Somewhere. I cannot find it. Yeah, I think. Yeah, I think you need to relate the element somewhere. Yeah, I think element somewhere. So I think what we need to do is e to the minus beta omega is replaced by the outer function omega minus n plus m plus mu by delta. You just write down this one is equal to e to the minus beta omega delta omega minus em plus en plus mu plus I delta. And then for first here you just m alpha 0 n. So by here you have n sine alpha b and then n squared. And then from here, so you just write that e to the minus beta omega is equal to minus en plus en minus mu. Like this thing. But I don't need down. You have to do like this transformation. So you integral omega integral, what you get is this one. And this one, and then multiply e to the minus beta en minus mu and n. You get that e to the minus beta en minus mu and n. Sorry, that's how you get it. Okay, so then everything possible. So you can derive this. Fine. Okay. So the spectral function is just the imaginary part of the retarded function. So now also the so G account is just obtained by G retarded. Just changing I delta to the minus I delta. That's the G account. So now for rho. Okay. And this can be understood as the okay. So then this can be understood as the 2 pi I G finite. Okay, I omega n, and the I omega n is replaced by omega plus I delta minus G finite temperature. Okay, omega n. And then I omega n is replaced by omega minus I delta. That's what you do. Yes. That's what you do. Okay. Okay. Okay, so then if you use this one, so you can just use the previous one. G R. Okay, I just go from this. So from there, so one can derive minus infinity rho k omega is equal to. I just got confused. How you? So I just want to show this one. But now, somehow I don't know how to show. Sorry, I just got confused. How do you show? I just want to show from here. But I got confused. How do you show them? Sorry. Sorry, I got confused. I don't know how to show that, to be honest. So this should be somehow related to, sorry. This should be somehow related to some minus infinity, omega 0, then omega double 0, then sigma, and proper normalization. Sorry. Sorry. It's just like this way. It should be done like this way, but sorry, this part I didn't prepare very well. Can anybody do that? Can anybody show how to show this in the one? From there. Oh, sorry. No. It should be so different. Oh yeah, it's very easy. Sorry. I don't know why. So we don't need this actually. Sorry. So we just use this plug this one. So this is the omega. What I want is the omega. Okay, and if you plug this one into here, what you get is d over dg. And sum of L and M and then E minus beta, E N minus zero, and N. And then plug this one into here, so what you get is like sigma E to the minus beta, M minus zero, and M. Okay. And then delta A plus KM plus KM 0. And then five 0 and right? And then this is exactly what we had before. So this is B over D, G is half over N, and then minus mu, then N, from the N equal to 0, psi, dagger 0, and N, and plus sigma, E minus there, E N minus mu, and N, M, sorry, M, N, and N, psi dagger of 0, and then psi, 0, and then this is plus M. Yeah. So this is equal to proportional to what? This should be proportional to something like a sigma 0, star dagger 0, and computational sigma and expectation value like this. And this should be equal to appropriate normalization should be something like that. I think that's what we need to do. Okay. I think some normalization. I think you need to be careful about some normalization. I didn't do it very carefully, which I didn't do it carefully. Yeah, I think you need to. Yeah. Be careful about this kind of stuff. I think you need to perform some kind. I think something like a Fourier integral of the delta function in spatial direction. I think that's what you need to do. But so if you do that, you get equal to 1. So you should get that equal to 1. Yeah. Okay. And unfortunately, I'm stupid that you raised to oh, okay. So if you use this relation, so this relation, and then this relation, somehow you get so rho of k. So this is equal to as infinity t omega 2 imaginary of the GR. Like this. And this is the start. Principal value divided by pi minus is the real of the function R. So you just apply real value of this one is equal to. So maybe I should one step. So 1 to infinity to infinity, e omega tilde, real value of rho k omega tilde, and the real value of omega minus omega tilde plus like that. And you use a sample area. Sorry, doesn't. And this is equal to it. So I use the fact that the rho of n omega is equal to minus 1.5 imaginary part of gr in omega, and also delta x. Sorry. Like this. So use two parts. To derive this is equal to this. So this P is the Cauchy principal body. So it's very nice that the real part of green function can be derived from imaginary part of retarded green function. So that's the and in field theory this will become so-called optical theorem. I'm not going to derive. So if you use this relation, you can derive so-called spell theorem. I mean, this time I'm not going to. So it's just common. It's just common. So somehow in common part of physics, this is called Kramer chronic. Relation. Okay. And unfortunately, I erased, stupidly erased. I erased the expression of the C here. Did I recover that? It's not so difficult to recover. And then the erase here. And new and energy, some of energy, and some we can get this B divided by B. So this used to be that. Okay. And then if I do this one. So if you use this one, so you can just imagine a part of green function of omega. Okay, so this is retarded one. So if you just write down, it's not retarded one. So if you just a green function, this becomes minus sign. This becomes minus sign. Okay. And they use this relation. So x plus I delta is equal to principal body of 1 over x minus I phi delta x, something like that. Apply this relation to here and here. Okay, here and here. And to get the imaginary part of green function, and compare with this guy. Compare with this guy. So what's going to happen is that, I mean, this is good exercise to do, but anyway, so 1 plus sigma e to minus beta omega, and 1 minus sigma e to the minus beta omega. Actually, that's what you get. And the rho is that's what you get. I hope people can see that. So rho k omega divided by 1 plus sigma e to minus beta omega. You just bring this one into here. This green part is the denominator. What's left is the e to this one and the delta function and this guy and this one. And then here, again, you need to be careful about the sign here. So you just get this one. You get if you apply this one, what you get is the efficient delta of this one, delta function. You got this thing. Delta. Okay. So this is x, right? So therefore, this is also x here. Exactly the same. And then so here you have a minus sign here. So that will give you this minus sign here, and the sigma, and e to the minus beta omega is that if you apply this delta function, you swap the role again here n and m. So reravel n and m extensively. Okay, and apply the delta function. So this delta function, so it becomes m like this one, and apply the omega into this value. So this part, e to the n minus the mu and n, becomes the what I'm saying. So okay, now, if you swap the role, so it becomes e to the minus beta, e n minus mu, yeah. So it becomes like this way. But if you plug this one into here, and then massage it, it becomes, at the end of the day, you become like this. So that's most important. So here, I mean, it's a good exercise to do. I mean, you just apply this one, and rewrite this to n and m, and then massage this part, and to bring it back to you. So that's what you need to do. Okay, so that's what you need to do. And this is equal to minus pi tangent of the beta omega over 2. Okay, spectral imaginary part of green function can be written by a spectral function up to this tangent, hyperbolic tangent. So the in field theory, it's better to work in the momentum space instead of coordinate space. I mean, here, if you just try to do the Fourier transformation, write everything in k and omega, you can find a very beautiful form. So that's very like when you do the QFT or static mechanics, most of the case you just work in the momentum space, because I mean if you do the momentum space, you can find much like the property of green function, whatever, it becomes transparent. Okay, that's why I mean in whatever course in mathematical physics you always learn Fourier transformation, because somehow physics, if you do the Fourier transformation, everything becomes more transparent. That's how somehow this world is created. Okay, using this expression, working again, you provide the GK. I mean, again, use this one. You derive this one. Combine them together using the tangent. Hyperbolic tangent is delta omega from the front row and omega cube. So here. That's what you get. Okay, like this like. Whoa. Okay, so that's what you get. I mean, the real part of G is the same as real part of GR. So you can use this formula. You can use this formula. So this is essentially real part of GR is the same as real part of G. Because of the green function, returning green function is the only sign different here in the output. So therefore, real part we can use this formula. It's 1 over omega whatever in with this rho. Okay. And the imaginary part is we already derived it. So you can, and you can just massage this a little bit. And this is equal to 1 plus tangent beta omega over 2 plus minus. Sorry, this is the sigma. And this is sigma. And this is sigma. Okay. G R plus 1 minus tangent beta omega over 2 sigma and G alpha. So, okay. Okay. Okay, and let's move on. And if you massage this way, it's just written as the 1 over 1 plus sigma e to the minus beta omega. And it's just very simple massage G part. And this is 1 over 1 plus sigma e to beta omega mg. Okay, so you can just write it down. So it's very, very nice. I mean, green function is the written in terms of theta t essentially, and this theta minus t. And so both combinations. So this is the theta t, and here you just have a theta minus t in contact. And somehow they are related. If you do the Fourier transform, they are related to like this very nice expression. But that's very expected because the G has contained both theta of t and theta minus t. Like here you have a GR of the theta t. So if you combine them, you somehow you can write down. Okay. Okay, that's what's happening. Okay, so the example. So G of retarded is the omega minus eta. It's a free field. So this is a free field. No interaction. So as you recall, G, it used to be G is the same thing. Blah, 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 blah. I doubt a sign of K minus K. It was like this. But now retarded is always plus here. And advanced is always minus. And the flat fixed relation, rho K, So what you get is what? Spectral function of, this is just delta function. Imagine about this side is this omega plus k. Like this way. So this means that if you have omega rho, it just becomes delta function. This is a free frequency. So on the other hand, the free field, so delta function, if you introduce in the Hamiltonian, if you introduce the interaction term, the spectral function becomes like this way. In the mod. So this can be understood density of state. State in omega space. In frequency space. You can understand that the spectral function can be understood as the density of state. Okay. That's what's really happening. Yeah, I mean here is EK minus mu. The function is EK minus mu. The delta function, but if you introduce interaction term in the Hamiltonian, so this delta function is blurred. Blurred becomes orange. Okay. So those are some property of green function of spectral function. And then to derive this relation, it is the Lehmann representation very essential. So that's one point. Okay. Any questions or comments? Now I just want to so far everything I can evaluate. So let me start. So this is important relation. So this is important to green functions. And also I derived very important this is also very important. And then this is very important. And then also this one is also important. So this is the essential summary of this today is that the anyway, so green function is the essential quantity, and it has the imaginary part and then imaginary part, real part, and then green function has usual green function, retallic green function, advanced function, green function. They are related by this formula, and the relation between rho and the green retallic part, imaginary part, retallic function, and so on are summarized in. So those, I mean, today's essence is this form, actually. Today's essence is this form. I mean, all those, whatever Fourier transformation level presentation is just to derive all those forms. So this is today's summary. Okay. I think so since this is board doesn't have the important formula for language. So far, we only consider H0 as a following thing. So H0 is something like a P squared plus N plus U of R, something like this. You always have this kind of H0. So this, but now we are going to introduce what about this R1 plus so we're going to do something interaction term. So this is interaction term. So we're going to introduce interaction term. And then to see what's going to happen. Okay. So interaction term, and then we're going to use so-called Landau Fermi liquid. So the next goal is to introduce the Landau Fermi liquid. Fermi liquid. Okay. What I'm going to do this. Okay. So let's recall the something very basic beforehand. So the ground chemical potential can be defined as follows. The omega is given by just recall the following. And the sum. And you can just put the following function. I mean, you don't need to put one. So just recall that the ground chemical potential is given by like this. This is really coming from E minus mu and M minus E plus exactly what we have. And let's write it down in terms of the modern language. Write down modern language. You learn is that the density matrix and this one can be understood as the omega is equal to price of raw fat and then H R minus B and R plus Bayer inverse log raw fat. Okay, so that's okay. And we used to so the rho. So rho here is given by it used to be something like this one. like this way. But now, so this, it's no longer H0. So as I mentioned, so we just change H0. H0 to H0 without potential. And I call this one H, future H. So this H is including this interaction term. Is that okay? So it becomes something like this no longer H0. We go like this. And then this, yeah. So important thing is that if you consider equilibrium, so if you consider equilibrium, so rho EQ, equilibrium is given by E to the value omega EQ minus H minus E. Like this way, and then rho EQ. Equilibrium is given by minus meters, and then log of rate of E to the theta H minus mu and I mean, here if you just transform it, what you get is that the E to E theta omega EQ is just rate of this minus theta H minus mu plus n. So this is a partition function from Tanaka. So this is the partition function of Tanaka. And the rho EQ is it's just a fixed. I'm going to erase the important formula. Okay. Okay. And then, so always we satisfy rho, sigma of rho is greater than omega, but not sigma. Omega of rho equilibrium. So this is the variational principle. So the equilibrium decimeters is minimized. This is the structure of compound. Plus and then so we introduce something Hamiltonian is given by now is this one x1 dx3 psi x1 and then 1 squared divided by 2 u r1 minus mu and then psi x1. So that's sorry, no, there is no here. So that in the lecture notes, instead of x1, I use the c, bi. Since they essentially encode information xi and the spin variable alpha. I mean, I changed the notation. I mean, maybe, or if you want, you can just, I mean, what I meant is that the psi ci is just a psi alpha I and xi. That's what I meant. That's a move. So I just suppress alpha and this notation into the x here. So I mean, but for the sake of time being, omega, let's just write that using the index. And then interaction time. So like this. So this is the Hamiltonian we have. Okay, and the decimeters here will have and be in the exponential of beta omega theta minus sum of q minus mu theta q mu q. And then omega theta is equal to sigma of beta sum of q log 1 plus sigma e to the minus beta q minus mu. Okay, so that's what you get from the previous. Okay, that's what you get. Recall that the so here what you have is essentially place h hat minus mu and hat. And so versus rho hat is the beta omega minus h hat and mu and hat. And then here instead of n hat, we use the fact that the so the CQ is the essential numbering operators, and then EQ EQ hat EQ is essential energy Hamiltonian. What I used to. And then rho 0 literally comes from used to be ground chemical potential. I mean, yeah. So yeah. So omega is equal to minus beta inverse of the log of the ground chemical ensemble. And we know that this is the ground chemical ensemble partition function. Is it okay? I mean, this is equal to okay, this is sigma, maybe sigma beta inverse, and then log of product of 1 minus sigma e to minus beta q minus 3, where q is. That I will just recall what we have done. So this is the what we learned before. I hope it's okay. So it's okay. Are you guys with me? Is that okay? And the plug it here. So that's what I do. But now the important difference is that so here epsilon q is no longer something like this one. So this the epsilon q is no longer it used to be something like this one. This is equal to eigenfunction of this one. On q is equal to this. It used to be. So this is the ideas and so on. We assume this relation. Sharing operator acts on this eigenfunction, you get the eigenvalue. But now we turn on this b here, so this is no longer true. Okay, this is no longer true, and we have to be be treated very nicely. And think, don't just be running out of time. So now we record the S is equal to minus rho hat, trace of rho hat log of rho. Okay. And let's plug this one into here. Trace of rho hat and log of rho hat e to the minus beta. Beta omega 0 minus log of q and from q and then dq and dq. And I don't need log again. Alright, dq and like this. Is that okay? Okay, and this is it's just this is just number. This is just number. Is it okay? Trace of rho hat unique is what? 1. Okay, so therefore this is minus beta omega 0. Actually, I mean if you want KBs, you can just KB. And the minus of q is from q minus mu. And then trace rho hat dq hat dq. So what's this? So this is equal to expectation value of this operator. And this operator is NQ. Okay? You get this. Okay, so that's what I'm getting. And then if you must say, sorry for running out of time. So I will derive this one. This one is KB sum over Q. It's very easy to derive it. Minus NQ log NQ plus sigma 1 plus sigma NQ and then log or 1 plus sigma NQ. I mean, so this is equal to N bar. And this is exactly what we saw in the ID gas. ID gas, we derived this one. I don't know, maybe you already forget about it. We derived this one. Entropy is equal to this one. But even interaction, with the interaction, we can derive this one. Okay, let's stop here. Next time, next lecture on Sunday. Be careful. On Sunday, I will derive this one and compare with ID gas. That's all.